Hello everyone, welcome back to my channel. Suhail this side. So this would be the 8th video in the Kafka Zero to Hero series. So first of all, I would like to thank each and everyone for showing love and support on my channel. So without wasting time, let's get started. Right. So today we would discuss why is Kafka fast. So just to remind you that this is the topmost question being asked in most of the interviews in most of the top companies. Right now, why is Kafka fast? We would answer this question in a very practical manner, like the videos which we have already discussed. Right, so the answer lies there only in the earlier videos, but I have tried to collaborate and to collaborate all the points, and we will discuss all the points and design decisions what Kafka guys has taken, which makes it actually fast. Right now, let's get started. So why is Kafka fast? Kafka is fast because of its efficient design and architecture, which actually optimizes disk IO, network communication, and data processing. Now, the words here might look very heavy words, which you might feel some discomfort to understand, but we would discuss each and every concept. For example, how the disk IO is optimized, how the network communication is optimized, and how the data processing is happening in the Kafka, which makes it actually fast. Let's see the design decisions, what actually makes it fast. Right, so the first design decision what Kafka has taken is the sequential disk writes. Right now, what it means actually, right, it means that Kafka appends message sequentially to the disk instead of modifying them in place, making disk IO much faster. Now imagine what happens actually. Right, so for example, this is the file. Right, so this is the file where the contents are being placed. These are the, you can imagine, the lines are in the file. Right now, as and when any update or any message comes, right, so the message gets appended at the last. Right now, if we have to append at the last, what we need to do, if you are doing it programmatically, just need to append the particular content at the last of the file. No need to read the particular file, no need to do anything, just we need to append the content into the file. Right now, this would be this would impact the greater performance benefit. Right, so modern SSDs and even HDDs are optimized for sequential writes. Right, so actually what happens internally, whenever for example you are writing anything, how the flow happens. Right now, actually you do the file dot write, for example in any of the programming language, where the call would go to the disk driver. Right, disk driver internally will call the kernel layer to write the content onto the file. Right, this is the actually flow. Right, you are not calling the disk driver directly, it is just abstracted at your side. Right, so you are just using the APIs which are being provided by the Java guys or the any programming language, but internally there are some calls which are being happen to the system calls. Right, which are being happen to the driver. Right, so disk driver actually. Right, so that's how your disk writes are being happening. Now let's understand this furthermore, let's deep dive into this more. Right now, for example, there is a producer and there is a consumer. So the how the flow would be, producer will publish some message onto the Kafka broker. Right, and consumer would retrieve message from the Kafka broker. This is the simple flow. Right, but remember, Kafka is a stateful application. Right, so if it is a stateful application, it has to store data somewhere, it has to store the messages somewhere. So where it is getting stored, in the log file. You can imagine the data file, log file. So you can imagine as a log file where all the data is getting stored. Now let's hypothetically take an example of, for example, some message, order message. Right, for example, the order update message comes, where it will go directly, it would directly go at the end of the file. Right, for example, the key is the partition key and the message is order 1. the value is order 1. Just for simplicity, I have taken this simpler message, but you can imagine as complex message as it is, but based on partition key, right? Now imagine next time there is a change in the order, right? For example, you added few more items to the order, or you changed the address in the order, or due to any reason the order update comes it again, right? For simplicity, just imagine the value is changed but the partition key is same, right? Now what would happen? There are two approaches in this case how we can uh, update this particular data into the file. Now this data is already written into the file, right, at the end of the file, right? But there could be chance that there are some contents which are more placed. For example, after this order 1 there could be some more lines would be there, right? Some more some more content would be there, right? Now for example, after this some more messages has come, and your order 1 is already there in the log file, but it is above the few of the more messages, right? Now what would happen? For example, let's assume no order 1 ABC comes, new message comes, right? Now how you can update this order? There are two approaches. Either you can do the in place update. That means in place update means, so you have to read the file, delete this particular message, for example the one colon order id. So for one, the value now is changed to be order 1 ABC. Now what you need to do, you need to delete the old entry and write the new entry, right? So in this case, in short, in simple terms, basically you are rewriting the whole file, right? So this is the first approach, right? The other approach could be that just append the new entry as it is, whatever is coming, just append the new entry in the log file. For example, the new entry comes, right? So you enter, for example, you enter at this point, you enter one order ABC, right? So you enter this at the last of the file, at the end of the file, right? So that is what Kafka guys has taken. So what they have taken, they have chosen the second approach, that whatever message is coming, just append at the last log file, at the end of the log file actually. Now you would argue there are some drawbacks for this second approach as well. Now you would argue, okay, that if we follow this second approach, though the size of the log file would increase like anything, right? So because it would increase, there is no other way, because you are continuously appending the entries at the last of the at the end of the log file, right? So but that is the trade-off they took. They are okay that if the log file size is getting increased, they are least bothered about that. They thought, okay, let it be. So they have optimized for throughput, because they don't want to rewrite the files again and again. So that is the trade-off they took. Now but the other thing, the drawback which you have mentioned, that what was the drawback? The log file size would keep on increasing forever. But how they solve this drawback? So they solve this drawback with a smart thing. So what they done, they have introduced the retention policy. That retention policy, for how many days you want to keep the data. For example, by default the retention period is 7 days, which we have already discussed in the fourth video in the Kafka 0 to Hero series. We have already discussed this, the retention policy, right? So by default the retention is 7 days. Now this value can be tweaked based on your business load, based on your application load, based on your criticality of the data, right? So you can change this setting. But they have solved this second problem, the drawbacks for this second approach, by this means, right? Now you would argue, okay, that why didn't they do the compaction of logs on the periodic interval? So instead of giving the retention policy, they could have done the compaction of logs. For example, now the entries are being inserted at the one order ABC is being inserted at the end of the log file, right? But after a periodic interval, let's assume once a day or twice a day, there should be some kind of background job can run, and which would actually obsolete the old entries, right? So you would argue like this can actually be happen, okay? But what they have chosen, they just want to keep the things simple. Why? Because again, compaction and the merging would also consume IO resources, right? Now imagine if they start using this way, if they start using compaction and merging of the log files, they won't be able to support high throughput. Why? Because your system has limited resources, right? So it has limited IO resources, it has limited CPU, it has limited memory. So the resources are not that much high actually, right? Now that is the key decision they have took. They have chosen a simple retention based policy that on which the data will be clean, because simple systems always scale, right? Now if you want to, the second thing is also the second thing, if they do the compaction, right? If they do the compaction, now let's say if you want to see the trail of the messages which have been published for the order, right? You won't be able to do that. Why? Because imagine if the compaction would have happened, the old entries would be deleted, right? Now how would you see that what is the sequence of the messages have been received by the Kafka broker? You won't able to do that, right? So now you can see lot of problems keep coming if you go with the compaction and merging of logs. So many new cases you would like to handle, right? So they just obsolete all the things, they just keep the things simple, very simple thing. They just offloaded this responsibility totally on the user. They have just introduced the retention policy, and based on that the data will be cleaned. So right, this is the first thing which this is the first design decision they have taken, that sequential disk writes would actually increase the performance, right? So that is the first decision they have took. Now what are the other decisions? The second decision, the major important decision they have took, I have done the benchmarking for this, I'll just show you there as well. So second design decision what they have taken, they have opted for zero copy architecture, right? So what actually is zero copy architecture? I have seen many of the senior engineers struggling here, right? Oh, I have written this program in Java, how I can call this kernel system call? Actually everything is abstracted from you, right? Everything is abstracted behind the the APIs, right? But internally everything is happening via system call. For example, when you do the file.read, this would also tell the disk driver to read the file from the disk, right? So Kafka, how it is achieving the zero copy architecture? First of all, let's understand what is zero copy architecture. This is very, very important, right? Now if you have seen my video on Nginx, right, how Nginx can handle 1 million concurrent connections, there I have explained in a very, very, very detailed way. But just to add on, I am just explaining what actually happens here when what actually zero copy architecture is, how these socket connections work, right? Now imagine this is a producer, right, and this is a Kafka broker, and this is a consumer, right? So what happens actually, producer, what it will do for producing the messages to the Kafka broker, there has to be a socket connection, right? Socket connection has to be established by a producer. Now for consumer to consume the messages, the socket connection has to be established by a consumer, right? Now what happens actually, and where actually Kafka is storing the data, it is storing in the log file, right, that we have discussed. Now what happens actually at the operating system level, every socket, this is the producer socket and this is the consumer socket, right? Now every socket has a read write buffer. Imagine this is a Java class, like you can imagine this is a Java class, for example the producer socket and the consumer socket. Now what actually is present in the producer socket and consumer socket, everything is linked with the file descriptor at the operating system level. Now what happens at the producer socket also has the read write buffer, and consumer socket also has the read write buffer, right? And the file descriptor, where actually to which file descriptor this socket is pointing to, so that operating system can get the particular connection associated with the particular file descriptor. That is why the file descriptor is needed, right? Now, first of all, what is zero copy architecture? Now, zero copy architecture means that the bytes which are being sent by the producer, right, is directly being written into the log file. Kafka is not loading into the memory, right? And similarly, what happens when consumer consume the records from the log file, the data gets transferred directly to the consumer socket, right, to the consumer socket, so that consumer can directly read the data from the log file. So that is the zero copy architecture means. Now let's understand how we can implement the zero copy architecture. Now, if you are using the Java IO package, right, what you have to do, you have to read the socket, right, and then write into a file, right? So it simply means broker has to read the data into the memory, into the process, right, and then only it has to open the log file, it has to write the data into the log file. That is the very simple use case. That is a traditional IO which generally many of the people doing, most of the engineers do this way, right? But what Kafka has done, Kafka guys has taken the java.nio package, right? So in this package we do have file channel, socket channel, right? So, and there are methods which are directly available there. For example, if you have to transfer from the producer socket to the log file directly, for example, producer socket to the Kafka log file, that message whatever producer has produced has to be directly dumped into the log file without Kafka reading it, right? Imagine, right? Now how you can do this? You can just simply use this file channel transfer from. This is the log file channel where the this channel is pointing to the log file, and from where it has to transfer from the producer socket. And this is the just the byte buffer which has been allocated for this producer socket, that how many bytes has to be written into this log file, right? So this is how simple is to implement the zero copy architecture. The whatever data is coming on from the producer, just directly write to the log file. Now whatever data has to be sent to the consumer, directly write from the log file to the socket channel, the other way approach, right? So that's how simple is it is. Now I would show you the benchmark as well, what I have done. So imagine this is the, I have used the JMH, Java Microbench, and if you see here, right, if you see here, that is the traditional IO. How we actually do the traditional IO? We are just reading the data into, means reading means we are reading into our memory, right, and then we are writing to the buffer, and then actually we are clearing the buffer. That is the traditional IO, right? Now what is zero copy IO? Zero copy IO is we are transferring from source channel to the destination channel directly, without copying it or without reading it into the memory. So this is the zero copy architecture. Zero copy IO actually means, for simplicity, for example, this is the input file, this is the output file, right? Input file points to the source channel, output file points to the destination channel, right? Now zero copy is actually what is doing, directly copying from the source file to the destination file. Now how this file has been populated, I have written the create input file, and in this input file I have just created the 10 MB file, right? So 10 MB file I have created every time in every iteration, and you can see every time whenever the benchmark is getting run on every iteration, the 10 MB file is directly copying to the output file. Now let's see the performance benefits for this. I have run this. So if you see the traditional IO, right, now you see how many operations we can do. 27 operations. That is the only thing, 27 operations. But with zero copy architecture, right, how many operations per second we are able to do that, right? 256 operations per second. Massive gain, right? Now these are just I have run for 5 iterations for 5 threads, but imagine in a Kafka, in a high cluster environment, right, where the the large number of requests are coming, and the throughput is like, you can imagine the, because this benchmark is getting run on my local machine, but actually if you run it on the Kafka cluster where the actually the cluster is being set up, you would actually get the high throughput, right? So this is much faster than the traditional IO. So that's, I will check in the code into the GitHub. I'll mention in the comment section as well. So let's see further. So that's how simple is to implement the zero copy architecture, right? Now the third decision is, what the third decision is, the batching and compression. So if you recall the episode 4, right, when we were producing the messages to the Kafka broker, we have seen some delay in consumer side when it was trying to consume the message, right? We have seen that. So why it was that? Because at that point of time also I mentioned producer tries to batch the records and on their own, and once it is done, and once it is done, then it sends the batch of records onto the broker. That's how it is being happening, right? And we have tweaked that particular parameter with the timeout setting. We have seen that we changed the timeout setting to 50 milliseconds, and after then we have seen that the messages are being consumed much faster. So this is a very crucial parameter for for production use cases, where we actually tweak this setting to get the more performance, or we have to do the more batching of the records based on, completely based on your application load, right? So producer do the batching on their own. By default it was 1 second, right? But you can tweak for how much duration you want to batch the number of records before producing to the broker. Now at the consumer side, there is a property like max.poll.records. At that consumer side, it would try to fetch these many records in a one shot, in a one single network call from the Kafka broker. So batching is happening at the producer side and at the consumer side. And also it supports compression like Snappy, gzip, lz4, so whatever, which actually reduces the bandwidth. Now the fourth design decision, partitioning, which we have discussed in a very detailed manner in earlier videos. Now topics in Kafka are divided into partitions, and each partition can be handled by separate broker. For example, these are two partitions. So one partition would be assigned to this, the other partition would be assigned to instance 2. So imagine for high throughput, if you have very high workload, you can have Kafka topic with the 100 partitions, 200 partitions, and if you have this much load, you can have, for example, 50 instances which can run parallel, right? So this would enable parallel processing across multiple nodes and consumers. So that was the fourth decision which they have taken. Now the fifth decision is Kafka consumer is the pull based model, right? Now Kafka consumers pulls data rather than brokers pushing it, right? Which allows consumers to fetch messages at their optimal pace, right? So it all depends on how consumers are processing the messages, right? And this would prevents the overwhelming consumers and actually optimizes the throughput, right? Imagine if Kafka broker, it starts pushing messages to the consumers. Okay, I have the new message, just get it done. I have a new message, just get it from me, right? So if this would be the case, no, so this would be much more problematic. And every time, imagine if there are, for example, 100 consumers or 500 consumers, so imagine 500 network calls to each and every time whenever the message is coming, right? So it would increase the it would actually decrease the performance, right? So pull based model the Kafka has chosen, right? Now the sixth design decision, the binary protocol. What is that? That Kafka stores everything in the binary format, which we have already seen. The serializer and deserializer is there, but at the producer and the consumer side, right? But whenever the data is getting transmitted to the Kafka broker, that is in the binary format. The serializer and deserializer is there, but at the producer and at the consumer side, right? Now this would make this design decision would make the Kafka perform faster, because imagine the text is much harder, because computers understand binaries, it doesn't understand the text. Because imagine the if it has to write the file, imagine if Kafka broker itself has to do all the serialization and deserialization logic, so the performance would be decreased. So that is why this responsibility is also offloaded to the producer and the consumer, right? Now replication and leader follower model. Now imagine this is a cluster, right? Kafka actually replicates data across multiple brokers, right? And how the data is getting written to the log file, actually the leader partition is responsible for handling the writes. The other followers asynchronously fetch the data, which would improve the redundancy without impacting the write performance. So that was the seventh decision they have taken. Now Kafka, with all these points, Kafka scales horizontally by adding more brokers, partitions, consumers, right? So if you need high throughput, if you see in a production that the producer is producing messages at a very high speed, but consumers are not receiving or processing the messages at a very rapid pace, like at the producer side. So you can just increase the consumer, or you can just increase the partitions, right? So it is totally horizontally scalable across all layers. You can increase brokers, partitions, consumers, right? Anything. So no centralized bottlenecks, right? Workload is distributed across multiple nodes. So all these optimizations actually makes Kafka capable of handling millions of messages per second with the low latency. So now next time if anyone says you that Java is not much fast, just mention that Kafka is written in Java only. So that's a very good example. If someone argues with you that okay, nowadays Java is finished, but the Go is doing great job, or this language is doing, every language has its own pros and cons, I'm not saying that, but Java is also a good language. And just give this example that Kafka is written in Java only. That was all I was trying to cover in this video. So in the next videos, we'll start with the Kafka cluster, and we'll see the design decisions. For example, if you have to set up the Kafka cluster for your organizations, on which parameters you can decide how many how much replication factor should be there, how much partition should be there, how much consumer should I have based on the message, right? So we'll discuss all this nitty-gritty details in detail. So thanks a lot, and please do watch other videos, like, comment, subscribe, share among other friends, and see you next video. Thanks a lot.